For decades, household electricity has been treated as a solved problem. The system exists, the infrastructure is widespread, and access is assumed to be continuous. Yet the underlying structure has not meaningfully changed. Energy is still produced elsewhere, transported across distance, and delivered through centralized networks that rely on uninterrupted coordination. Most households interact only with the final layer of this system, the outlet, the switch, the monthly statement. The complexity that enables this simplicity remains largely unseen. When disruptions occur, whether from weather, demand spikes, or maintenance, the system's fragility briefly becomes visible. Then, once stability returns, it fades again from attention. Over time, several responses have emerged to address this fragility. Some focus on temporary redundancy, backup generators, battery units, or emergency plans intended for short-term interruption. Others emphasize efficiency, aiming to reduce usage rather than address dependency. There are also large-scale solutions promoted at institutional levels, often requiring significant investment, space, or regulatory involvement, placing them outside practical reach for many households. Each of these attempts addresses a portion of the problem. None fundamentally alter the household's position within the broader energy structure. The persistence of the problem is not due to lack of innovation, but to structural alignment. Most energy systems are designed around centralized production and linear distribution. This model prioritizes scale, predictability, and administrative control. Households, however, exist at the edge of this system. They have limited influence over production, routing, or recovery timelines when failures occur. As long as energy remains something that arrives from elsewhere, dependence remains embedded, regardless of efficiency gains or temporary safeguards. This is the structural boundary within which most solutions operate. Outside the dominant model, alternative formats have periodically appeared. These approaches do not necessarily replace centralized systems, but reframe how energy can be captured, converted, or used within smaller physical and spatial constraints. Some draw inspiration from biological systems, environmental geometry, or nonlinear collection methods. Others explore form factors that differ from flat, surface-dependent designs traditionally associated with energy generation. These alternatives exist largely outside mainstream adoption, often remaining experimental, niche, or informational rather than standardized. Their presence does not resolve the problem, but it complicates the assumption that only one structural model is possible. Within this broader landscape, some products have emerged that document or formalize these alternative formats. One example is a system referred to as Solar Innovator, which presents a nature-inspired approach to energy collection through a three-dimensional form factor. It is not positioned as a replacement for existing infrastructure, nor as a universal solution. Instead, it represents one interpretation of how energy generation might be structured differently at a small scale. Its relevance lies not in performance claims, but in the fact that it exists at all, illustrating that the prevailing model is not the only conceptual framework available. The problem of household energy dependence persists not because it is ignored, but because it is structurally complex. Most solutions operate within the same foundational assumptions that created the issue in the first place. Alternatives exist, but remain peripheral, unevenly understood, and rarely integrated into everyday planning. Whether this changes is not a question of awareness alone. It is a question of which structures are maintained, which are explored, and which are left unexamined. For now, the problem remains, not unresolved, but ongoing.